Hello everyone, and welcome back to my channel. Well, it's time to do some serious ultrasound. So I have purchased a high-end ultrasonic microphone that is good for picking up ultrasound frequencies up to 150 to around 200 kilohertz. So here's the box, and its frequency response graph is shown on the this first page of the I don't know if it's called, if it's, this is a packaging slip, or I guess these are the specifications. So I'll just zoom in on it and you can have a look. So this microphone is by Avisoft Bioacoustics, and its frequency response is from about, according to this graph, is from about 10 kilohertz all the way up to 150 kilohertz, which I believe should do very well for what I'm trying to do. I doubt if I can pick up any frequencies of ultrasound above 100 kilohertz that can travel more than a few feet through the air. So let's have a look at what's inside the box. Okie doke. Here we go. So this is the microphone itself. Here we are. A condenser microphone type. Model number CM16/CMPA. And what else do we got here? This is the microphone biasing unit, which this microphone requires 200 volt bias voltage to operate. So that's what this unit does. 5 volts goes into one of these pins. One pin is ground. 2 of the pins are outputs, has a both inverting and non-inverting output that you take to your own amplifier. And comes with a couple of cables, a long cable and a short cable. And let's have a look. Here we go. So this is the short cable. That will do very well for connecting it to the circuit board. And the wires, here they are, they're all labeled. So we have a 5 volt wire power supply to the microphone, the ground, and the positive and negative outputs. And it connects up to it's an XLR type connection, and it connects up to the biasing unit like so. Nice. And what else? We have a microphone clamp and a mini microphone stand that I can stand up on the bench here while I'm testing it. Okay, so put that aside for a moment. And what do I have for testing this high-end microphone out? Well, we'll get to that right now. I have also bought some ultrasound transducers. So I have, starting from the lowest to the highest, let's see if I can find them. There we go. 25 kilohertz transducers, which they'll both act as a source of ultrasound, and also they'll act as a microphone. The thing is, these tend to be tuned to one frequency, so they'll transmit efficiently at one frequency and pick up at the one frequency that they're tuned to. So these are piezoelectric transducers from STEMinc, STEMINC. Okay, that's the 25 kilohertz. I have a 40 kilohertz. Incidentally, they're not all the same size. The 25 is much larger than the 40. And I have a 60 kilohertz. And I also have an 80 kilohertz transducer. So, and in addition, I have a tweeter speaker from an old speaker, stereo speaker. That all of these can be hooked up to the function generator, and we'll see how well that microphone that can pick up frequencies up to 150 kilohertz does with these ultrasonic sound sources. I think these will do much better than the wine glass I was tapping in previous videos, but of course the fun won't be complete without tapping the wine glass. So we'll get to that as well. But this is the more of the serious scientific experimentation we'll do is with these transducers and the tweeter. So I'm going to briefly describe the amplifier circuit for this new microphone. And basically it's a single op-amp that accepts both inputs of the microphone, negative and positive inputs. It provides a gain of about 20 dB for the resistor values shown on each of the inputs, and we'll see if we need to take that down or take it up as we go along. And so, since this is a single supply circuit, I have a biasing voltage divider on the positive pin of the op-amp, which biases this point here at about halfway of the power supply voltage. So for DC operation, since I have these capacitors here, which are, I think they're about, I have them set to about 0.15 UF. They are DC blockers, and they basically remove the rest of the circuit for DC. So you can that gives you an idea how this thing works for DC biasing. And for AC, of course, they're like short circuits, as if they're a continuous connection. Okay, and then we take it to the scope from pin 6. We also have a DC blocking capacitor there, just to remove the DC component, because we're only interested in the AC sound. So what does it look like on the breadboard? Well, here it is. Nothing too dramatic, but that is essentially it before I connect the microphone. So the microphone I'll be connecting with the wires shown. I have these pigtails already spliced on at the outputs, the ground, and the power supply. The microphone takes 5 volts, whereas the op-amp will be taking 12 volts provided there. So I still have to provide a 5 volt power supply voltage to the microphone. I might just take it on this strip, which is free. at the time being. Okay, so let's hook this up. Incidentally, yeah, here's the microphone, and I am using the long cable instead of the short one. I just couldn't make I could not make the short cable fit into the microphone clamp. So there it is. So now what I'll do is I'll measure the output produced by the little test amplifier for the microphone. There it is. The microphone's all hooked up on the breadboard using the various sound sources that I have. The first one being the old tweeter speaker, and what I'll do is it's already wired in, connected to the function generator. I'll feed it various frequencies at different voltage amplitudes. I'll point it at about 24 inches away from microphone. There it is. And what I'll be doing is I'll be measuring the output level of the function generator, which is going to be set at a fixed level. I'm going to be measuring the voltage at the input to the speaker, because the speaker has an impedance that changes with frequency, and the function generator has a fixed output impedance, 50 ohms, that the two of them in combination will act as a voltage divider. So the 5 volts on the display here, oops, get it to focus, 5 volts of the output on the display will only appear if I have a very high input impedance on the speaker, which probably for this moving coil speaker is not going to be very high, but it'll be somewhere in the range of 8 ohms or so. On the ultrasonic transducers, their input impedance is probably much higher, and we'll probably get much more of that voltage appearing across their terminals. I'll set up the camera on the tripod and point it at the oscilloscope. So I got 2 traces, yellow trace being the output from the amplifier, and the pink trace being measured directly at the sound generating source. Well, here we have the 1 kilohertz tone applied to the speaker and pointed right at the microphone, about 24 inches away. So the voltage appearing at the speaker is about 720 millivolts. The input voltage is 5 volts directly from the function generator. And the amplifier, well, maybe it's just noise, but it's only producing 100 millivolts of output at 1 kilohertz. I'm writing all these figures down. So as the specifications suggest, this microphone really does not pick up much below 2 kilohertz. Okay, I'm increasing the frequency to 2 kilohertz. Oops, there, 2 kilohertz. Okay, I have the 80 kilohertz transducer connected, and 5 volts set for the generator, 4 volts appearing at the transducer terminals, with 4.98 volts, almost 5, at the amplifier. So this is another large one with a large surface area that's capable of producing more sound. Yeah, that about sums it up. This microphone is very capable of picking up ultrasonic frequencies. So So just to wrap up this video number 6, it would be prudent to compare the performance of the Avisoft Bioacoustics microphone against the Electret, what it was, 44 something or another, just to see how they stack up when it comes to responding to high frequencies. So I have the Electret microphone, there it is on the breadboard, and a little amplifier for it. So what I'm going to do, I'm going to use the function generator, 2 channels of the function generator, and I'm going to feed 1 channel to the tweeter speaker and set it at 10 kilohertz as a tone that I'm sure both the Electret microphone and the Avisoft microphone can pick up. And then the second channel of the function generator, I will feed to one of my, where is it? There it is. I will feed to one of my ultrasound transducers. Well, actually, I'll feed it to both, more than one. I'll start off at 25 kilohertz transducer and move on to the 40 kilohertz transducer. And what I'll do is I'll aim both of these, the speaker and the transducer, at the Avisoft microphone, and then at the Electret microphone in turn, and then measure the response to the 2 tones on the oscilloscope. So what we should be able to see there, if I were to calibrate the output of the function generator such that both the 10 kilohertz tone given off by the tweeter and then the tone that's fed to the ultrasound transducer, if I set them at equal amplitude by varying the output level on the function generator to achieve equal amplitude on the oscilloscope, then if I aim it to the Electret microphone, I should be able to see the change in response of the Electret microphone to the 2 tones relative to the Avisoft microphone. So that will basically tell us how well or how bad the Electret performs to a couple of test tones in relation to the Avisoft microphone. Okay, so let's get started. Okay, I have the tweeter speaker pointed at the Avisoft microphone, and it is producing a output voltage of about 3 volts if I, on the amplifier that is, if I were to aim it there it is, if I were to aim it about correctly, and the peak corresponds to about the 0 dBV mark on the spectrum there. And now if I were to turn off the tweeter and turn on the transducer at 25 kilohertz, I also have a peak of about 3 volts output on the amplifier. So they're about set to 0 dBV, thereabouts, equal outputs, calibrated to produce equal outputs. Okay, so now we'll repeat this procedure for the Electret microphone. Okay, I have the tweeter speaker aimed at the electret microphone, and the gains of the two amplifiers, Avisoft and the electret microphone, are not exactly the same, but I believe I'm getting, if I would stop speaking, about 580 millivolts of output. It varies quite a bit, but it appears to be 10 dB below the 0 dBV mark on the oscilloscope. So 500 millivolts. Okay, so I'll switch off the tweeter and turn on the transducer at 25 kilohertz. 480 millivolts, hovers around, but the two peaks look about comparatively the same. So it's more or less at 25 kilohertz. It performs about as well as the Avisoft microphone. Okay, I have the 40 kilohertz transducer now calibrated to produce about 3 volts. Let's see if I can aim it at the Avisoft microphone. It hovers around between 2.5 and 3. It's doing about 3 volts. And just for comparison, the tweeter speaker, .76, 2.9 volts. So they're about more or less set to produce almost equal. So I can bring up the tweeter speaker output a little bit more. Okay, so this is the electret microphone producing an output about 1.4 volts. There's the peak at 10 kilohertz, and it's also picking up my voice. That's why there's all those squiggles and wiggles in the spectrum. But if I be quiet, and there's some harmonics as well. It's obviously not a clean output from the tweeter, but the one of interest is about at 10 kilohertz. Okay, so let's switch on the transducer. There's the transducer output. The 40 kilohertz at 40 dB V below the 10, well, minus 40 dBV, yeah. And just for comparison purposes, let's see the output amplitude of the tweeter. It's about at minus 10 at the 10 kilohertz spike. So this electret microphone has a loss of about 30 dB at 40 kilohertz relative to the Avisoft microphone. And let's see if we can turn both tweeter and transducer on at the same time, just for the comparison. You can see both peaks. Yeah. Aside from some harmonics, the spike at 40 kilohertz is definitely about 30 dB below the spike at 10. So yeah, this electret microphone definitely will not work for detecting bats. So let's conclude these tests with a wine glass ringing, singing, just like we did in one previous video, to see how much of the high frequencies of the wine glass this microphone will pick up. Okay, I'll set the scope for single time trigger and give the wine glass a bang. Oh, didn't get much there. Do it again. Well, there's a nice trace. That definitely, first of all, let's explain where we are in space here. So 20 kilohertz is right there. We're looking at the Fourier spectrum of the wine glass amplifier output, and we have 20 kilohertz right about there. 25 kilohertz is the center point of the screen, and as you can see, we're way above 20 kilohertz. We're picking up, I guess these will be the resonant frequencies of the wine glass, and here's a nice big spike that occurs at, okay, this 25, divisions are 5, 35, 45. At 45 kilohertz, we have this wine glass singing. Quite a wide spectrum. So that's much more than we could pick up with the that little electret microphone that I used previously. Let's do one more, see what we can get. Yeah. With each tap, you don't necessarily stimulate the same resonant frequencies, but there's definitely resonance frequencies at around the 45 kilohertz mark. Much higher than what we can hear, anyways. So this microphone is, I think it's working very well.